Okay, hello everyone. So I am Mateusz, and today we'll be talking about font security, about reverse engineering font rasterizers, finding bugs in them, and exploiting the bugs that we find. So I work at Google at Project Zero, and I'm basically interested in all sorts of low-level security, basically like software vulnerabilities on the low level. I have a blog that I sometimes write to. You will definitely find the slides from this presentation there, so if you're interested in that, be sure to check it out. And today, we'll be mainly talking about PostScript fonts specifically, so Type 1 fonts and OpenType, which is the newer version of Type 1. And I will try to tell three stories. First one, how I basically got into looking into font rasterizers on the example of a free type vulnerability that I found last year. Then I will talk about the Charstring research, which is basically a research into the security of an OpenType and Type 1 virtual machine or a state machine that is implemented in many places in programs that we use every day. And the last story that I'm going to talk about is very recent. It's about font fuzzing and how I found several bugs in the Windows kernel by basically just flipping bits and doing similar stuff in both OpenType and in TrueType. And I will also cover some bug collisions that came out of this. So let's start with a very short introduction into Type 1 and OpenType fonts. So we're on the same page. Basically, PostScript fonts were created by Adobe like 3 decades ago. So they introduced 2 outline font formats, which was a novelty because previously everyone was using a raster formats, which was just bitmaps of different glyphs in specific point sizes. So they introduced outline font formats called Type 1 and Type 3. And Type 1 is the one that we're really interested in because it's the commonly used one. So it's a kind of font that uses PostScript programming language and more specifically a very concrete subset of the specification. And when they were introduced by Adobe originally, they were very proprietary. Closed, the documentation was closed, so no one really knew how it worked, or if they knew, they actually had to reverse engineer it first. So it was only documented in March 1990 because of the fact that Apple created another font format called TrueType, and they were actually forced to open the documentation for Type 1. So the format of the font itself, when it comes to Type 1, is very simple. You basically have like a set of dictionaries, and the dictionaries can be nested. So you can have other dictionaries inside, and other than that, you have different values which can be of type string or number or array or boolean. And the last type of things that you can have in the dictionaries are charstrings, which are basically the programs that are executed by the font engine, which are responsible for actually drawing the outlines of the glyphs. So it's pretty simple overall. And here we have an example of what a charstring looks like. So it's basically like a PostScript program, as I said. So it's instructions, PostScript instructions interlaced by like immediate values that are basically operands to those instructions that they operate on. So other than that, the charstring execution context basically consists of the instruction stream that I just shown, which is a stream of encoded instructions, because they are not in the file, they are not in text form, they are in binary form. So they are not accessible by itself, so you cannot have like self-modifying code and stuff like that. You also have an operand stack, which is where the immediate values that you saw on the previous slide are basically pushed before they are taken up by the instructions to operate on. And it can hold up to 24 numeric entries, which are 32-bit each. So yeah, and then you have the third thing, which is the transient array, also called build char array, and it's just a temporary array for the PostScript program that you can access randomly, so you can read from it and write from it, and write to it, and you can control its size through one of the characteristics of the fonts. So when it comes to the charstring operators itself, you have like several groups of them. So you can divide them by function, You have commands for starting and finishing an outline, for construction paths, for hinting, for performing arithmetic operations, for calling subroutines and stuff like that. And you also have like a large range of bytes that are just used to actually specify the immediate values. So this is a screenshot from the official specification of type 1. You can really see that there aren't too many instructions in the type 1 specification. It's just a few of them, and you have like an escape command that specifies some extended commands, but it's still pretty few of them. What should be noted is that the type 1 format specification was basically changing very dynamically. When it was introduced, it contained a specific set of instructions, but then Adobe has been releasing like further iterations of the specification, removing some of them and adding further ones. So it's very important to keep that in mind. And you can actually see that in the previous screenshot because you can see the gaps between the identifiers of the instructions. So some of them are actually missing that have been there in the past. Another interesting thing about type 1 font files is that you actually have to have several of them to actually be able to load a font in the system. So for Windows, it's a minimum of 2 files with the PFB and PFM extensions, with PFB being the actual core of the font file, and PFM storing the metrics of the font. And you also have a third file that you can optionally use to load a font, which is related to multiple masters. And multiple masters are basically like an extension, which was introduced by Adobe in 1991. So what it does is that it enables specifying 2 or more like font styles that you can interpolate between to create like fonts with a varying degree of width, height, optical size, and stuff like that. And technically, it's just implemented by introducing several new dictionary fields and several new instructions that you can use in the programs. This is an example of how this would look like. You could basically have like a continuous set of different like properties of the characters. So multiple masters as an extension was supported by Adobe Type Manager, which is the software released by Adobe to actually rasterize the fonts. It was the first program to properly rasterize type fonts on the screen. But unfortunately, multiple masters was not really commonly adopted worldwide, and this was partially caused by the fact that OpenType, which was a newer format, was adopted worldwide, and it basically took over the market. So overall, there is only like 30 official fonts that are commercial and 8 further free ones that you can find on the internet that have multiple masters inside of them. So yeah, it's very unheard of. Most people don't know about it, but it turns out that some softwares such as Microsoft Windows and the kernel and Adobe Reader still support it for some reasons, compatibility probably. So when it comes to OpenType, it was released by Microsoft and Adobe in 1997 to supersede TrueType and Type 1 fonts and create a format that was basically like combined all of the good features of the 2 formats. And the major differences in comparison to Type 1 is that it only requires a single font file with the OTF extension, as you probably know. All of that previously textual data, so all of the dictionaries that you had in Type 1 fonts were converted to a compact binary form so that the files would be smaller, and the Charstring specification was extended dramatically. So here you can see how the set of instructions that are supported in OpenType, and it's obviously like 2 or 3 times more that you saw on the previous screen. So the changes include new instructions for calling global subroutines. You have new instructions for like hinting related stuff. You have, most importantly, very useful instructions such as arithmetic and logic ones, so you can add, subtract, multiply values on the stack and stuff like that. You can interact with the operand stack in different ways, so you can duplicate values on the stack, exchange them, get nth value from the top of the stack and stuff like that. You can even have an instruction that puts a random value of the stack. I don't know why you would need like a non-deterministic value for font rasterization, but you have that instruction too. And you can also operate on the transient array that I talked about earlier. So it's a lot of new stuff in OpenType. And if you read the documentation thoroughly, you can also see that they actually pointed out all of the implementation limits of a proper font engine that you have to keep in mind when writing one. So this is a very good starting point for actually doing any kind of vulnerability research, because you can verify then that each of those limits are actually being considered and properly handled by the font engine that you're looking into. So let's start with the FreeType bug. As you probably know, FreeType it's probably the best and the most commonly used open source font rasterization library. It's written in C, which is very convenient for us as bug hunters. It's highly efficient and portable and used everywhere because its clients include like Linux, iOS, Android, Chrome OS, and many other popular platforms. So, and it also supports a lot of basically all existing formats, such as TrueType, OpenType, but also the less known ones, such as BDF, PCF, and stuff like that. So as you can guess, since it's written in C and supports all of those formats, it's the perfect attack vector. And I guess this is true, and people have noticed this in the past as well, because, for example, Comex used a bug in FreeType to implement a part of his exploit chain for the iOS jailbreak MiV3, and even won a Pony Award for it in 2011. And people have been finding quite a lot of bugs in the project overall. So you can look up in any vulnerability database that there are a lot of entries for FreeType. So I've been fuzzing it myself since 2012, and I've found like over 50 bugs myself by just fuzzing it. So it's really full of bugs. Obviously, not everyone was happy about it. But yeah, so at some point in 2013, I got it to a fast, clean state obviously with my then current method, so with my corpus that I had for fuzzing and with my mutation algorithms. But after a while, I saw that Adobe would be contributing a new font rasterizer for OpenType CFF. And so first they proposed to contribute the code, and they pushed it to FreeType, and it was not enabled in the default configuration, but people could test it out. And after another month, it was basically enabled as default in FreeType. So this was a completely new piece of code that you could find bugs in, which got me very excited. So it included, of course, a lot of complex and interesting code, because CFF and the OpenType charstrings are very complex. Unfortunately, most of the useful operators in charstrings were not really supported, as you can see. And I guess this is a good idea, because those instructions are not really used in realistic fonts. So I guess most of the time they are actually really useful to an attacker and nobody else. But it was still very extensive, and there were still many assumptions in the code that one could probably try to break. So I restarted the fuzzer with OTF files against the new code, obviously compiling my harness with other sanitizer, and I didn't have any results for a few days. But then I actually encountered a very interesting crash. This is like the log from other sanitizer, and it says that there's a stack buffer overflow condition overreading 1 byte. And you can see this in the stack trace that there are functions like CF2 interp to T2 charstring, for example. So this obviously is related somehow to parsing charstrings. So let's look at the bug itself. The function that the crash occurred in was CF2 hint map build. So the relevant piece of code is shown on the slide. Basically, here you have a declaration of a structure called temp hint mask of type CF2 hint mask rec. This is the important part. It's in line 758, and then you also have the bit count variable initialized in line 796, which is a controlled value. So the definition of the structure is as follows. The important part is that you have an array called mask, which is a byte array, and it has 12 bytes, which is 96 divided by 8, because it's basically a bit mask for storing 96 bits. And this number comes directly from the specification, because it's the number of stem hints that you can have at maximum. So this is where the bug was actually triggered in the code. You have a loop iterating from 0 to bit count, where bit count is a fully controlled value. And the crash originally occurred in line 820 because of the fact that the mask pointer was referencing outside of the local mask buffer. But then you have a controlled expression value inside of an if statement, and if you can get it to be true, then you can also turn off specific bits outside of the buffer in line 850. So the vulnerability was basically caused by like an obvious lack of sanity check for the stem hint count, which should have been limited at 96. And it resulted in out-of-bound read and write operations outside of the local buffer that was 12 byte long. So it made it possible not to control any byte specifically, but to clear any chosen bit on the stack. So it's kind of difficult to exploit. It's more difficult than just writing anywhere, but it's still possible. And also the interesting part is that it's a non-continuous override. You can actually choose which bits on the stack you can clear. So you can just jump over the stack cookie and just override the return address or any other value on the stack that you want to get actually like remote code execution. So the trigger for this inside of the Charstring is very simple. You just have to invoke the hstem instruction a sufficient amount of times, which has to be more than 96, which is the legal size. Then you have to have a vstem instruction called at least once to have a valid hint map, and you have to trigger the bug using the center mask instruction. So here is an example of how an exploit could look like to actually change the return address of the CF2 hint map build function. You're just executing a lot of hstem instructions until you go out of the mask buffer. So you then go through the stack. At some point you reach the stack cookie, but you also jump over it. And once you reach the return address of the function, by controlling the arguments of the hstem instruction, you can just clear specific bits of the return address. So here we're just clearing off like the most significant byte of the return address, right? So we're clearing the bits. Once we do that, we just execute a few more instructions to actually trigger the bug. And with the enter instruction, we're leaving out of the function and triggering the overwritten return address, and we get a crash. So if you look at the code, you could see that there was a very interesting comment in line 795, which said to do compare this to CFF hint mask get bit count. So this sounds a little bit like to do add security. Unfortunately, it wasn't the root cause of the bug, because it's a little more complicated how it looks like in the code. But the author of the code still seemed to realize that something might go wrong there, and they wanted to add a safety net to check that a wrong condition wouldn't happen. The extra comparison would only be a safety net, but it would prevent the bug from being exploitable. And it's a good thing to keep in mind, because there might be some other like to do or XXX statements inside of the code that might indicate that there is some interesting behavior or a bug in there. So the timeline of the bug was that I discovered it in February and reported it on 25th of February. It was patched in Git 3 days later, and then a few more days later it was also released in a stable version of TrueType. So the test case stopped reproducing, and the bug didn't pop out anymore in my fuzzing, so I thought it was fixed. But like a few months later, I had a better corpus and a better mutation algorithms for fuzzing, so I restarted TrueType fuzzing, and it turned out that the bug was still there, reachable through some other code paths. So yeah, it wasn't really good. I reported it again on 21st of November, and as I said, it was the very same bug, which you could also see here. It also indicated itself in the very same way. So it's been improperly fixed for 9 months, and it was only properly fixed in December last year. So that was actually the first bug that I found in fonts, and it got me interested in the subject. So I started looking into char strings and how they are implemented in different software. And being a Windows fan, I obviously started with Windows. So in Windows, the driver that is responsible for Type 1 and OpenType fonts is called Adobe Type Manager, which has been present in the operating system for many years. It's been there since Windows NT, basically, or 2000. It was contributed by Adobe to Microsoft, so it's actually Adobe's code and not Microsoft's. And the most important part about it is that it's used in many different software, so it's not just Windows GDI, but the very same code that Adobe contributed to Windows, it's also used verbatim in Adobe Reader, in DirectWrite, which is a library used to rasterize fonts in user mode by document readers and web browsers and stuff like that, and it's also in Windows Presentation Foundation. So this means that if you find a single bug in OTF handling, that's in one of those engines, that it's very likely that it's also in the other software as well. But there is some good news. While the code base of those font engines is common for them, it was only the same like 20 years ago, but since then different teams and different people have been managing it at different companies, so they might not be affected by the same set of bugs really, because they have been receiving various degrees of interest by the security community. So some bugs might have been fixed in some software, but not the other. So that's good news, right? But it's also bad news, because if you can bin-diff those software or cross-diff them between each other, then you can possibly find bugs in some software that's already fixed in the other one. So it's not a really very good situation, I guess. So the idea that I had in mind after seeing how extensive the code for handling the charstring was, that I would just manually audit all of the code of the state machine and see how many bugs I could find. So, but before I could find any bugs, I definitely had to reverse engineer the driver itself, because it's not open source and you don't even have symbols for it, as I will tell you here in this slide. So Microsoft Symbol Server doesn't have the symbols, even though they provide them for other components of the operating system. So we just have to stick with just generic names that IDA generates. Maybe that's the reason why it was less thoroughly audited as compared to, for example, Win32k, which handles TrueType fonts. I don't know. But it's also good to note that since the code base is shared, maybe the symbols would be shared as well. For example, the library in Windows Presentation Foundation called Presentation CFF Rasterizer Native blah 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 has symbols. Maybe we could port them somehow to the ATMFD driver. And as it turns out, well, this is a valid way, but there is also another way. So as Halvar Flake noticed, many years ago, Adobe released some builds of Adobe Reader 4 and 5 that would have symbols included, including the CoolType driver, or the CoolType library, which is the library responsible for font rasterization. So since the code hasn't really fundamentally changed since then, we can just take some symbols by comparing the functions and move them to our ATMFD analysis, and it should work fine as well. Yeah. So when we do the basic recon of the ATMFD driver, even though we don't have symbols or anything like that, we still have debug messages, because Microsoft didn't get rid of them during compilation. So we can deduce many things from it. Apart from the behavior of the code itself, we can also find out variable names, both global and local ones, function names, because they are often referenced verbatim in the messages, conditions that they checked for in failed assertions and stuff like that, even source file paths, which can also help us in some way. And there are also many type 1 font string literals too, which means that if there was a specific part of code that would be handling a specific part of the type 1 fonts, then we would be able to easily identify it in the code as well. So here you can see some examples of those both debug messages and string literals that I found very useful when doing the reverse engineering. So when we try to find the function that is actually responsible for executing the Charstring programs, it turns out that it's not very difficult to locate, because for one, it has a lot of references to those debug messages that I mentioned before, like really a lot of them. And also, incidentally, it's like the largest function in the whole file. It has over 20 kilobytes, a single function with 20 kilobytes of code. So it's like, it's 5 times larger than the second function in the module. It's quite large. Here's how it looks like when shown as an IDA graph. So, yeah. So that's the interpreter function, and we can also confirm that this is actually the function by looking at direct write and Windows Presentation Foundation when it's called type 1 interpret charstring or do type 1 interpret charstring, something like that. That's a definite proof that we're looking at the right thing. And as you saw in the previous slide, it's just like a giant switch case statement handling all of the instructions that they support in the function. So the overall structure of the function is, as I said, just a switch case. So they just read like a byte of the charstring instruction and then handle all of them in different blocks. The question is why the function is so large, and the answer is that first of all, it handles both type 1 and type 2, so OpenType charstrings, in the very same function, because the two specifications for those instruction set are actually compatible with each other. So type 1 doesn't use any instructions that type 2 uses, and vice versa. And also, very conveniently for us, ATMFD actually implements every single feature that was ever part of the specification of either type 1 or OpenType, even if it was only for a few months and then it was deleted like 20 years ago. It's still there, supported by ATMFD. So that was my reaction when I saw that. So let's get to work. I will not be talking about the process of reverse engineering ATMFD further, but we'll just discuss the bugs that I found there. And I will start with the very simple ones, just to illustrate like the quality of code that I saw when I started doing the research. So first of all, we just have like a denial of service that only affected Windows kernel, which was by the way the worst module of all of the shared code bases. Most bugs were found in Windows kernel. So let's think about what is the stop condition for executing charstrings. When does the interpreter loop stop? And the answer is that either you have to have an end char instruction that is encountered and then all the execution is stopped, or when there is any error condition detected during execution of the PostScript command, the interpreter also just aborts and returns from the function. But there is no hard limit over the number of instructions that you can execute. And even though there is no loop support, contrary to, for example, TrueType, you have subroutine calls. So you can just create like a large tree of subroutine calls of depth 16, for example, and at the bottom of it, you can have like some CPU extensive instructions executed so that it will execute forever. So it's a very simple bug. It allows you to take up 100% of one CPU, and you can use multiple fonts to block multiple cores. And the process couldn't be killed on Windows because the thread would remain in kernel mode all the time. So yeah, that's just a simple DOS for the Windows kernel. But it already tells you that they didn't really consider too many of the corner cases that someone would want to attack. So the second bug, which is also quite simple, which affected both Windows kernel and Adobe Reader, is just out-of-bounds reads from the charstring stream. It's also very simple. So the charstring stream, the stream of instructions, is accessed by the interpreter in several situations, either at the beginning of the VM execution loop in order to read the main opcode, or while reading the escape opcode, or when reading an immediate value to push on the operand stack. So in none of those cases, the function would actually check if it's not overreading the buffer, the source buffer with the charstring. And there are two different memory regions that the function reads from when actually parsing the charstrings. It either reads from kernel mode pools, if you were loading a type 1 font, or from the userland heap of the CSRSS process for OpenType fonts. So we have two scenarios in that case. We could either try to disclose some memory from the CSRSS process if we're lucky, because the parser would overread the buffer and would start reading garbage, or uninitialized or leftover data, and then reflect them in the glyph somehow. And it was actually observed when I set some of the charstrings to be like regular charstring drawings and glyphs, and then some of the other ones would be just empty, then the empty ones would reuse the memory of the previous ones, so they would be also drawn as the regular glyphs even though they were empty. But otherwise, it's just a very difficult condition to exploit to extract any meaningful information from the stack. But on the other hand, it's quite easy to use this bug to cause a blue screen of death, because you just have to create a char string sufficiently long that it reaches a page boundary and actually stops at the page boundary. Because if we have a char string that ends at a specific point in memory and then you have some zeros or some other values outside of it, then the interpreter would most likely just abort at a specific point before reaching the boundary of the page. But that's viable to accomplish, and I've actually managed to trigger this condition, so you can have a blue screen of death. And it also shows you that they didn't really care about any conditions that could cause some harm. And here it's also important to note that in ATMFD you have a very interesting piece of code which just wraps all of the code that is responsible for doing char string interpretation with a large exception handler. So if there is any exception generated inside of the interpreter caused by an invalid reference to user mode memory, then Adobe, the ATMFD model would just not care and graciously handle the exception and pretend that nothing happened. So I don't know the reason for that. Maybe it's just a poor man's way to maintain system stability, because the driver would overread buffers from user mode memory so frequently that the system would crash otherwise. I don't know. But it definitely disrupts like dynamic vulnerability research, such as fuzzing, because if there was ever a condition resulting in invalid user mode memory access, then the people doing the fuzzing would never actually find out about it, because the system would never crash. So that's something to keep in mind. Then there was another easy bug, Windows only. So if you look at the stack frame of the interpreter function, you can see that there is a local array called OP_stack, and that is the actual original symbol taken from the debug messages. And it is used to store all of the PostScript operands inside of it. And then we have a pointer which moves inside of this buffer. So the most charstring instructions actually operate on some operands, and they expect the operands to already be on the stack. So ATMFD originally didn't do anything to actually verify that these operands were on the stack. They would just assume that enough values were pushed beforehand. So consequently, we could get the interpreter to access some dwords from the stack before the OP_stack local array, as you can see here. Up to 3 dwords before the array. So there have been quite a few of these overreading instructions. You could overread or actually underread memory in many different ways. But the sad things is that at the beginning of each iteration of the loop, the interpreter would actually check if the pointer was not below the array. So even if we executed the instruction and it would overread some bytes, then at the next iteration of the loop, the interpreter would bail out anyway. So it's not very useful. The only exception is the dupe instruction, which was over or under read 4 bytes and then push them again on the stack. So we could disclose 4 bytes of the kernel stack before the local array, but that's not very useful either. And then we also had some overriding instructions such as not, neg, and so forth, which would follow a common scheme of first popping the operands from the stack, then performing some operations on them, and then pushing them back. So this could be potentially remote code execution because we're under reading on the local stack with some instructions. But in practice, it turned out that the 2 dwords that we could access before the local array didn't really contain any interesting information. But that's just purely coincidental. And it's also illustrative of the code quality of of the function. And then we're getting to the interesting stuff. So we have a memory disclosure bug via uninitialized transit array. And this bug is interesting because it affected all of the programs that use the same shared code base, and even some other ones, such as Oracle Java, that is not on the list. And it could be triggered both using type 1 and OpenType fonts. So as I said before, the transient array is basically just a temporary array of dwords that can be accessed from Charstring programs randomly, and you have instructions that read and write to it. In type 1 fonts, you could fully control the length of the array by using a len build char number entry, which was 16 bits long. And in OpenType, the length of the array is actually constant. It's defined in the table that we saw before, and it's equal to 32 elements. So the array can be accessed using a number of instructions. The most interesting ones, which are supported everywhere, are get and put, but there are some other ones that also access the array. And if you look at the code, or actually in the code used by Microsoft 5 months ago or something, the array would only be allocated on the first access, so it wouldn't always be allocated, only when the interpreter would encounter an instruction operating on the transient array for the first time. And it's allocated from the kernel pools in ring 0, or in case of, for example, direct write, it's obviously the user mode heap. So the question is, what happens if we try to read from an entry that hasn't been previously written to? The specification actually addresses this matter explicitly. So they have this sentence saying that this behavior results in undefined behavior, which is always a good thing to read in specification. And as you can guess, here undefined meant that it's old bytes from reused memory region. So the allocation wasn't zeroed out prior to letting the charstring operate on it. And that meant that we could read some uninitialized bytes from the transient array into the operand stack and then perform some operations over it. And it's good for us because this dword could be then easily drawn as a glyph, and the contents of the memory that we read could be reflected on the screen and then somehow read back. It's not really trivial, but because of the fact that the specification has so many instructions that let you perform arithmetic and logical instructions, you can implement this. So with OpenType, one glyph can disclose 32 dwords, as I said, because that's the length of the transient array. With type 1, you could control the size of the transient array that you're leaking bytes from. And it was possible to disclose memory from Internet Explorer, Windows Presentation Foundation, and the Windows kernel with the very same bug. Unfortunately, or fortunately, Chrome and Firefox, even though they also use direct write, which was susceptible to this bug, they use a project called OpenType Sanitizer, and it's a very small library that sanitizes fonts prior to having them fed to external font engines, and it prevented this bug from being exploited. So it's kind of like another one bug to rule them all. And here I would like to show you a demo of an exploit for Internet Explorer. So let's pray to the demo gods that it works. We have a HTML document with the proof of concept. So yeah, you can see here that we're rendering two glyphs. One of them is a synchronization glyph, which just has like a grid of bits enabled and disabled, and next to it is the actual glyph that leaks data. So you can see that when we refresh the web page, we get different results. And I implemented some simple heuristics to actually detect addresses that are disclosed through these leaked bits. You can see here, for example, in the first 4 bytes of the disclosed stream, we get an address inside of direct write. I can also confirm this by running vmmap. So the address is 7333. So let's look for it here in vmmap. Okay, actually the screen is too small with this resolution for me, but believe me, it's in address within the right. So yeah, this is the exploit working here. So we could basically use it. Yeah, to defeat ASLR in Internet Explorer. So then we have some bugs that actually allowed like elevation of privilege and remote code execution. This one was a read and write what were in the load and store operators. It was a Windows kernel only bug. And it was related to something called the registry object, which was defined in the specifications in 1998. And it was related to multiple masters. But then it was removed in 2000 from the specification, but ATMFD still, of course, supports it now. So the two instructions related to this are store and load, and they can transfer data from between the transient array and another storage object called the registry object, which is indexed using a value and can be either value 0, 1, or 2. And this is the best part of this specification. It says that trying to address using an index other than 0, 1, or 2 is undefined. So internally in ATMFD, the registry items are implemented as an array of registry item structures. This is my name. I don't know how this is called internally. It's just the length of the structure or the data buffer and then a pointer to it. And even though the kernel tried to verify the index, as you can see here, there was a comparison over the index. It didn't do it properly. So as you can see, they checked if the value was larger than 3, and it's not supposed to be 3, so we have an off by 1 condition. So using the load and store operators, we can actually trigger the memcopy calls from registry item 3. We could either read from the data pointer or write to it, provided that the size field of the out-of-bounds structure would be greater than 0. And the registry array is just a part of the overall font state structure, which is many bytes long. And it turned out that the third item in the array was actually uninitialized during the interpreter runtime. So we could spray the kernel pools such that we could control both the length and the data pointers inside of the structure. And then we would have arbitrary read and write capabilities in the Windows kernel. So triggering the bug is very simple. We just have to have 5 instructions, 4 operands to the store instruction, and then the store instruction itself. And if we actually did the pool spraying properly, we could trigger the following blue screen of death by trying to write to the AAAA address. Then we have another bug, which was a pool-based buffer overflow, both in the kernel and in Adobe Reader. And it was caused by a bug in counter control hint, which was another very obscure part of the specification. So we could provide the font engine with an arbitrary number of hint parameters in packets of maximum of 22 integers using a mechanism called other subroutines. So yeah, the kernel basically just allocated a constant sized array for those counter control hints and didn't perform any bounds checking over the actual number of integers that you tried to write to it. So with enough sequences of the one that you can see here, you could just overflow the buffer with any data you wanted and any size you wanted. For example, here you can see an example of using nested subroutines calling each other in order to have many 414141 bytes written outside of the allocation, resulting in the following bug check. So you can see it's an attempt to read outside of the page boundary with the buffer. And then there was yet another buffer, this time not overflow but underflow, that was also in both Windows kernel and Adobe Reader, in a mechanism called the store vfile instruction, otherwise known as other subr 19. It's not really known by anyone, I guess. It's not documented anywhere, but most font engines support it anyway. Maybe it was part of a specification at some time that I couldn't find it. So the usage of the instruction is as follows. It just takes an index and then the invocation of the instruction itself. and it requires a wide vector dictionary of length up to 16 to be present in the top dictionary. So the instruction would copy the contents of the wide vector into the transient array, starting with index IDX, which we specified, which is obviously popped from the stack. And it's popped from the stack as a signed 16-bit value. So before copying the data, the interpreter would also try to check that everything was fine and we wouldn't really overflow anything. But it turns out that if you specify a negative value for the index, you could still cause an underflow of a maximum of 64 bytes. Yeah, so you could basically have the following memcopy to execute with IDX equal a minimum of -16. So for ATMFD in the Windows kernel, this would mean corruption of the preceding pool headers or possibly the allocation that was before it. And for Adobe Reader, corruption of Adobe's internal allocated headers. So this is how Windows would crash upon triggering this bug. So yeah, we then have the last bug, which was a out-of-bounds stack manipulation via the blend operator. I think I'm actually going to skip it because I already documented it quite well during my recon presentation in June, and you can read about it in the previous slides pretty well. So the interesting thing about this bug is that it allowed you to create an exploit that was fully reliable because you could operate on the stack with all of the OpenType and type 1 instructions, including the arithmetic ones and stuff like that. So you could just create a ROP chain fully reliably by just constructing it at runtime without any external help from any scripts or stuff like that. Yeah. So here is an example of how you could, for example, by using the blend operator, just exchange the save EBP with the return address on the stack and then have the function return causing an attempt to execute non-executable memory, which was the stack, the saved stack pointer. So now I'm going to talk about font fuzzing a little bit, which was my latest feat. And even though the Charstring interpreter was a perfect manual code audit because it had many features that made it possible to find all of the bugs in it, because it was self-contained, it was just a large function that I could just scroll over in Hexrise, for example, or IDA. It was relatively simple format of processed data because it was just the binary encoded PostScript programs. It didn't have any references to itself and stuff like that. It was very simple. I knew what problems I would look for inside of it and assumptions I could violate. And if you think about it, it would be really difficult to find any bugs inside of Charstring interpreting by using fuzzing. So it was really much more effective to do it by hand. But it's unlike the general font security research because overall, if you look at the fonts, they contain like vastly complex data structures. You have many tables that reference each other and you have many connections between the data inside of it. And it's often non-obvious and you have to learn many things about fonts and stuff like that. So it's also an extensive quantity of code. So even though I could read all of the interpreter's code within a month, I couldn't do the same thing within a year probably for the general font parsing. So fuzzing is definitely a better approach here if you want to be time effective. So font fuzzing, as you know, it's like the common hotness in InfoSec because everyone thinks about it at some point or does it at some point. And likewise, most of the bugs that are actually used in the wild, I suppose, are found through fuzzing. And the best thing is it still works. So one of the examples is the TTF vulnerability that was used to escape Sandbox during this year's Pwn to Own, exploited by the Kin team. So I've been resisting this for years because on the premise that if so many people have already done it and found bugs, they probably found everything. But I finally gave it a shot in May this year. I did some dump fuzzing of TrueType and OpenType, also of TrueType because of the fact that they are fundamentally the same. They share the same SF and T structure and have many common tables and stuff like that. So I applied some simple tricks to actually make it as effective as possible. I generated a good corpus of input files that I would mutate both for OTF and TTF with maximized code coverage and minimal size. I would run this code on like many machines. Also, because of the fact that there are different tables inside of the fonts and they have different kind of data inside of it, I applied per table mutation ratios instead of just doing the same mutation ratio for all of the font because it doesn't make sense. I used a number of different mutation algorithms and combined them to mutate the fonts. I also developed a Windows harness that would render all of the glyphs inside of the font but not any other ones in order to not waste any cycles. I did everything in memory, so I wouldn't do any disk I/O at the time because this would also consume a lot of cycles unnecessarily. I would use the special pool mechanism and also optimize Windows such that the overhead of the operating system itself would be very small. So this, after a couple of days, this resulted in 7 OpenType bugs and 4 TrueType bugs discovered in the Windows kernel caused by mutations in various tables such as glyph, gpost, and stuff like that. And initially they were all scheduled for the August Patch Tuesday because they were found in May. But then on 20 July this year, I saw that there was an out-of-bound security bulletin released by Microsoft, which credited myself and also 2 other people. And it turned out that it was a collision with Hacking Team. So they've been using the same OpenType exploit to escape the sandbox on Windows, which was discovered by the guys that were also credited by Microsoft. It was specifically in the font parsing because the first ATMFD bug that they used was in the interaction from user mode to kernel mode, but this one was specifically in the parsing of the font, which was a pool-based buffer overflow, which they leveraged to get a privileged escalation. And also what's interesting is that it was the most commonly hitting OTF crash during my fuzzing, so that was just like the most low-hanging fruit they could find and use. The condition that they used was shown here. It was just an overflow of 32 bytes. So they would assume that a specific field inside of a structure, which was 16 bits, would not be 0. And if it was 0, it would copy an excessive number of bytes. So as you can see, the condition itself was also very easy to find because it was just sufficient to set 2 specific bytes next to each other in the file to zeros in order to trigger the bug. So it's super easy to find this through fuzzing. So the details of the bug were discussed in several places by several different people, and they also wrote exploits for Windows 8.1, 64-bit, and other platforms. In essence, that they just put another object with a vtable directly after the overflown buffer, such that they could point the vtable into user mode, and from there they could execute ROP to disable SMAP and then run arbitrary code with kernel privileges in user mode. So the last batch of fixes, so the 10 remaining bugs were basically fixed as planned in the August Patch Tuesday, and at the time another bug collision turned out to have taken place with Keen Team this time. So it was one of the bugs that was used during Pwn2Own. I also found it during fuzzing. And the culprit of the bug is related to the IUP instruction. And you can also see that basically the condition that could lead to this was also specified verbatim in the specification of the TrueType instruction set. So the trigger for the bug was also very trivial. It was sufficient to just flip one specific bit inside of the TrueType instruction stream, and then you would see a blue screen of death. So the conclusions and data points from the second collision is that, well, many bugs that I have shown here could really be found inside of the specification itself. So it's not very difficult to find them. And it's very useful to actually look at the specification when doing vulnerability hunting. And it's interesting how these vulnerabilities made it until this year with such trivial triggers, right? Everyone could find them very easily. And yeah. Also, the bug was also the most frequently hitting TTF crash that I had, so it was also low-hanging fruit. So for the future of fuzzing, there's still some things to be done. You can have less dump, more structure over mutations. You can use code coverage-driven fuzzing, which I didn't do. You can have better memory corruption detection ratios. For example, you can somehow deal with the fact that ATMFD and also Win32k have this very aggressive exception handling involved that hides some of the conditions that you would be interested in. And you could also have fully generative fuzzing for some portions of the specifications, for example, the TrueType VM. So you can also expect some more font bugs to be fixed soon in some common products. And when it comes to final thoughts overall about fonts, turns out that they are not extinct, even in 2015, even though they should be gone a long time ago. So, but it's quite the opposite at this time, as you could see here, and I think it's doubtful that they will completely get extinct anytime soon. So the best thing you can do is just remove them from any context that are privileged and that the attacker could use to actually like get either remote code execution with any privileges that he could use or to elevate his privileges in the system. And one good move that Microsoft did to actually address this was to move font rendering out from the Windows kernel into a very limited user mode process. So this would prevent the exploitation of some of the bugs. Also, shared native codebases still exist, and they are immensely scary in the context of software security because on the example of the blend bug that I didn't have time to talk about today, you could exploit it to both get remote code execution in Adobe Reader and then use the very same bug to escape the sandbox. And these code bases are especially interesting for file formats that were written many decades ago. So even this year, one good bug suffices to defeat all of the high quality mitigations that are used on our system nowadays. This is the last thought. So with that, thank you very much, and I am happy to answer any questions afterwards.